For this problem, we have a solid sphere rolling along the ground at some speed here of v, and it's going to end up rolling up a hill and eventually coming to a stop. And we want to think about, first of all, the energy transformations that happen as it goes from here while it's rolling to up the hill and finally coming to a stop. So let's go ahead and draw our energy bar chart here. So initially the wheel is moving, so it's going to have some amount of kinetic energy. Like that, we'll say it's 3 bars. It's also rotating, so it's also going to have some rotational kinetic energy. How exactly you divvy it up, we could figure out the exact ratio, but we're not going to worry about it. The important thing is that it has both types. There's no gravitational potential energy, no springs here, so we don't have to worry about that. And then when it gets to the top of the hill here, what it's going to have left is it's going to have just gravitational potential energy, because when it gets up there, it's going to come to a stop. And so all that kinetic and all that rotational kinetic is eventually just going to become gravitational potential. Equation-wise, deriving an expression for that maximum height, we're going to think about conservation of energy here. E initial plus work equals E final. So we initially have kinetic and rotational kinetic, and that's going to be equal to our gravitational potential that we have at the end. So 1/2 mv squared plus 1/2 I omega squared equals mgh. There are 2 key substitutions we're going to make here into this equation. First, the moment of inertia for a sphere, which is 2/5 mr squared. The second is that velocity is r omega, so we're going to say that our angular velocity is v over r. So we'll make those 2 substitutions here into our equation. So we have 1/2 mv squared plus 1/2 times 2/5 mr squared times our angular velocity, which is v over r, but since it's squared, it's really v squared over r squared, and that equals mgh. And the reason we need to do this is we need to answer in terms of v and fundamental constants. While there's nothing wrong with omega by itself, we don't know what the angular speed is, so we're going to get rid of it. So the masses there cancel out. This r squared and that r squared also cancel out. What we're left with here on this left side is 1/2 v squared plus 1/2 times 2/5 becomes 1/5 v squared is equal to gh. And so we end up combining those, and it becomes 7v squared over 10, and we divide by g, so 7v squared over 10g is equal to our height. For this question, we have 2 spheres with the same mass and radius, but one of them is a hollow shell and the other one is solid, and we want to think of a way that we can determine which one is which. So there's a number of ways of doing this. I'm sure people will come up with some other ways, but one very, very easy way that I can think of is to take both of the spheres and roll them down a hill. Okay, and the reason why that will work is the one with the hollow shell, all right, is going to have a greater moment of inertia. Even though it's the same mass and radius, because more of the mass is on the outside, its moment of inertia will be greater. And because of that, more of its energy will become rotational kinetic energy and less will become linear kinetic. And so that means that the solid sphere will make it to the bottom of the ramp first, and the hollow sphere will make it down second. And that's how you can determine which one's solid, which one's hollow. For this next one, we have 2 conceptual questions related to rotational kinetic energy. So in the first one, we have 2 objects, a box and a hoop, that start from rest at the top of a ramp. We want to know which one reaches the bottom of the ramp first. If the box slides frictionlessly down the ramp while the hoop rolls down the ramp, or if the incline is frictionless for both objects. Okay. So if we think about this energy-wise, for the box, it starts with gravitational potential energy at the top of the ramp, and as it slides frictionlessly down to the bottom, all of that gravitational potential becomes kinetic. So we can say mgh equals 1/2 mv squared, and so its velocity at the bottom is proportional to the height that it initially had. For the hoop here, we start with gravitational potential energy once again, but we're going to end with kinetic and rotational kinetic at the bottom. So what we're left with is mgh is equal to 1/2 mv squared plus 1/2 I omega squared. So we end with two different kinds of energy. And that's the reason why the box is going to beat the hoop down the ramp, because of this rotational kinetic energy term. That means that not all of the hoop's gravitational potential energy becomes kinetic. We can't say that the velocity is directly proportional to the height because of this extra term here. All right, so that means that at the bottom of the ramp, the hoop will be traveling slower when it reaches the bottom, and therefore will take longer to make it to the bottom. The second part of this question asks if the incline is frictionless for both objects. How does that change things? Well, if the incline is frictionless, that means that the wheel won't actually roll at all. It's just going to have linear kinetic energy. It's going to slide down the ramp without rolling. And so its energy is exactly the same as the hoop. It starts with gravitational potential. It ends with kinetic. The height is going to ultimately be proportional to the velocity, since those masses would cancel out. It actually doesn't matter the mass of either one. And they'll end up traveling at the same speed at the bottom, and therefore they'll reach the bottom at the same time. For question B here, we're looking at this situation where there's a ball rolling along a level ground. It's going to roll up a ramp with friction and come to a stop at a height of h up here. And we want to know how that height would change if the ramp was instead frictionless. So it's a similar idea to the last one. I'm going to think once again about my energies. So in the case of the ramp with friction, we have kinetic energy and rotational kinetic energy being transferred into gravitational potential. In the case of the ramp without friction, what's going to end up happening is there's not going to be any torque in order to change the rotational speed of our object. That's what friction does. It provides a torque to change the rotational speed of our object. So we're going to start with kinetic and rotational kinetic, and there's going to be a force converting that kinetic energy, that linear kinetic, into gravitational potential, but we're still going to have rotational kinetic energy. And because of this term here, it means that not all of our energy is converted into gravitational potential, and therefore we won't reach as great of a height. For this problem here, we have a wheel with a mass of m and a radius of r. It's a thin hoop, so the moment of inertia is mr squared. It's initially at rest and held in place about its axle. We have a torque applied to it as shown in this graph, and it varies in magnitude from 0 to tau over an angular displacement of 2 theta. And so the first thing we want to do is derive an expression for the angular speed of the wheel after rotating through a displacement of 2 theta. So what I'm going to do, the thing that I'm going to start with here is using this graph. All right, we got to know this. This is a big idea, that the area under the curve there on that graph equals the work done on the wheel by that torque. Okay, so I'm going to break this up into two parts, a triangle and a rectangle, and I'm just going to go ahead and solve for that work, and then I'll worry about how I'm going to use that. So for the first segment, area is base times height, so it's just going to be tau times theta. So that's the area of the first segment. For the second one, it's a triangle, so 1/2 base times height. So it's going to be 1/2, the base is theta, the height is tau, so 1/2 tau times theta, which means my total work done is 3/2 tau theta. Now that I have that, I can go ahead and set up my conservation of energy here, and I can use that work that I just solved for to figure out what the angular speed of this wheel is going to be after rotating through that amount. So we're going to say E initial plus the work being done equals E final. There is no initial energy because it's not moving at all. The work being done we just found was 3/2 tau times theta. And we end with rotational kinetic energy 1/2 I omega squared. We're looking for angular speed, so we're not going to make a substitution there for omega like we've done for some of the other problems. But we do need to substitute in for I because we don't know that. However, we do know that I is equal to mr squared. And so we can make that substitution there. The 2's on the bottom here cancel out. We can go ahead and move some things over to ultimately solve for omega. So we're going to have 3 tau theta divided by mr squared. That's what omega squared is equal to. So we'll just take the square root there. Now we have our answer there for part A. For part B of this problem, we're going to think about now placing the wheel gently on the ground. So it's initially at rest here, some very minuscule height above the ground, and it's going to then transition to rolling smoothly along the ground, and we ultimately want to solve for its linear velocity. We do know, and this is important, that it loses 1/3 of its initial kinetic energy in the process. So that's going to be some work that's done on our wheel as we place it on the ground. So I'm going to think once again about E initial plus work equals E final here. My initial energy is that initial kinetic energy that I had, so I could go ahead and do 1/2 I omega squared, but ultimately it's going to give me an initial energy of 3/2 tau theta. So I'm just going to use that for my initial energy because that work that I did became my initial kinetic energy, and so I'm just going to say that that initial energy was 3/2 tau theta. Plus some work being done, we're told that we lose 1/3 of our energy, so I'm going to say negative 1/3 times 3/2 tau theta. That would be showing that loss of 1/3 of our initial kinetic energy, and then we're going to end here with kinetic, linear kinetic, and rotational kinetic. So on this left side of the equation, 3/2 tau theta minus 1/3 times 3/2 tau theta, that's really just minus 1/2 tau theta, gives us tau theta as our initial energy. Afterwards, we have kinetic, so 1/2 mv squared plus 1/2 I omega squared. Here we are going to make two important substitutions. The first is we're going to substitute in for that moment of inertia. We know it's mr squared for our hoop. And the other is we're going to say that our angular speed is v over r. We're ultimately looking for our linear speed in this situation, and so we do want to get rid of that angular and replace it with our linear. Since it's squared, that v over r becomes v squared over r squared. The r's, of course, go away, and what I'm left with is tau theta equals 1/2 mv squared plus 1/2 mv squared. That's what this term becomes. And so it really just simplifies to mv squared, and we can then solve for v dividing by mass and taking the square root, and we get tau theta over m. The square root of that quantity is our linear velocity. For this problem here, we have a merry-go-round that's initially spinning at some speed, and it has a kinetic energy, a rotational kinetic energy that is, of k. A person exerts a torque on the merry-go-round, causing it to speed up. And that ultimately doubles its angular speed. And the first thing we want to do is how much work was done on the merry-go-round in terms of k. And so here's what I'm going to think about. This is kind of like one of those new and original problems. So our original situation, we had k was 1/2 I omega squared. We now doubled that angular speed, and so k prime, our new angular speed, is going to be 1/2 I times 2 omega, that quantity squared, which ultimately becomes 1/2 I times 4 omega squared. I'm going to pull that 4 out in front here, and so k prime is going to be 4 times 1/2 I omega squared, which is my initial kinetic energy. So that means that my new kinetic energy is just 4k, 4 times my initial. Now that I have that, I can solve for my work by using conservation of energy. E initial plus work equals E final. The merry-go-round starts with an energy of k, its initial kinetic energy. Some amount of work is being done, and we end with an energy of 4k. So that means that the work done in this situation was just 3 times k, that 3 times that initial kinetic energy. For B here, we want to think about how much torque was exerted on the merry-go-round, knowing that that torque was exerted over an angular displacement of theta. So we know that work in the angular world is just torque times delta theta. Our work done was 3k, okay, and we know that it was done over an angular displacement here of theta, and so we can solve for that torque. That's just going to be 3k divided by theta.